Okay, so this lecture is about figuring out what type of a Haskell expression or functional expression is. We're still working with a kind of a small subset of Haskell, but this works for lots of things. So, for example, suppose you're given a definition of something like kxy is equal to x. How can you figure out the type? So what we do is we start with guess with a guess. We guess and we say, okay, look, if this thing is going to be well typed, then x is going to have some type. Call that type A. Label x by the polymorphic type variable A. Label y by b. It could turn out that they are going to turn out to be the same type, but let's start off assuming that they could be different. And then we have on the right-hand side of the equal sign, over here to the right, we've got x is the only thing in this program. You give it two arguments and it returns that first one. So we labeled all the x's and y's over here underneath by the polymorphic type variable we've chosen. And now it turns out our goal is going to be that this right side, even if it's a much more complicated expression, boils down to one type. And it turns out here's the single type expression on the right. So just by writing down this in this form, we can see that, okay, K has the type, you take A and that arrow, B, and that returns finally an A. Okay, what about something more challenging? So you might have tried on a previous homework to figure out the type of the S combinator. And the S combinator is written SXYZ, and I'll write it over here because I've put in all the parentheses here. It's normally would say, SXYZ is equal to XZ YZ, because that's the minimum number of parentheses, but to make this thing correct. But I think adding back in the parentheses doesn't hurt. So since function application associates to the left, we know that XZ applied to this is actually X applied to Z, and then the result of that applied to YZ. So here's all the parentheses, and I think it can help you avoid getting confused if you add them all in. So here we did what we did on before. We labeled, we picked an A, B, and a C. X gets labeled with A, Z is C. Okay, so you have to be careful. Y is a B and Z is a C. So here's our first row. Now, if you look at XZ, X is applied to Z, and since X has, since Z has type C, that's what we see in this column here, is that Z has type C. It must be that we don't have the type of X correct, because X must be a function that maps C's to something. So X : A is not correct. X must be something of the form C arrow D. And how did we get D? Well, we don't know what it maps to, so we just say, okay, X must be a function. It's got to map a C somewhere because it's applied to a C if it's going to be well typed. We don't know yet, so look over here and say, okay, look, D is a type variable that hasn't been used, so now we write down a new row, and we replace all the A's by C arrow D. And so we get this new row here. Now this rule is called the arrow introduction rule, because you can see we added arrows into the new row. And it says, look, if I have some term applied to some other term, so in this case, E1 is X, E2 is Z. If E1 is labeled by a polymorphic type variable, say A, and in this case it really is labeled by A, and E2 is labeled by type expression, say tau, and in this case tau is just C, A must really be a function of the form tau arrow alpha, where alpha is a new type variable, like we picked D here. So you make a new row in the table, and by copying the last row, and then replace all occurrences of A by tau arrow alpha. And our tau was C, and our alpha was D. Okay, so now, we're in the situation here on this is the row that we just created, where we look at it and we go like, oh, okay, wait a minute. We've got I'm missing a parenthesis here, a C arrow D applied to a C. So X is a C arrow D, Z is a C. Well, that's going to give us back just a plain old D, because D is what you get. If you apply a function that maps C's to D's and you apply it to a C, you get back a D. So we put a D in there, and we combine those two rows by adding in this D here, by replacing them by D. Combine the two column elements here for X and Z by labeling it with D. So now what we know is that XZ must have type D. And that's, of course, given the assumption that X has the type C arrow D, and that Y has the type B, which we had in the previous row. So we get this new row where we can combine those two things and simplify the right side. Okay, now, this rule in general is called arrow elimination. And it basically says, look, if you have in the top row an E1 applied to an E2, and E1 is labeled by a tau arrow tau prime, so that's our C is tau, D is tau prime, and then E2, which in this case is Z, is labeled tau. Okay, so now the C matches up with the tau arrow tau prime and the tau. Then we create a new row combining the columns for E1 and E2 by copying the last row. Copy the last row and insert the type tau prime, which in this case was D, for the combined row. I don't know, maybe it would help if I show how this rule is instantiated there. Okay, E1 is equal to X in this case. E2 is equal to Z in this case. E1 has type tau arrow tau 1, so tau is equal to C. Tau arrow tau prime. Tau prime has type D. And E2, Z, is in fact labeled with C. And so now we create a new row, and we replace the type tau prime, which is D, for the combined row. Okay, so now we'll look again and see what rule might apply. Now, since XZ we just decided was has type D, and it's applied to YZ, we might think that arrow introduction applies. Just change this D to a, but the problem is we don't actually have an actual type expression for YZ yet. We're building one. So it's not labeled, YZ is not labeled by a single type expression. But YZ itself is a good candidate. So we look over here, we go like, oh wait, YZ has type B, a C, so it's a good candidate for applying the arrow introduction rule. Okay, so we look over here and we look at this and we go like, okay, we've got a B arrow, B followed by C, but so B must really have been is equal to some C arrow E. And so we replace B everywhere it occurs in this row. We place that B and we replace this B by C arrow E. Now we can do the arrow elimination rule to get YZ simplified. And so we look at, we've got C arrow E applied to a C, and so that just becomes an E. And so now we have a DE expression. And now we can do the arrow introduction rule again. We go like, well, wait a minute, D can't just be a D. It has to be something of form E arrow F because it's being applied to an E. So we replace all the D's here by E arrow F. E arrow F and E arrow F. Now, you have to go back, and part of this rule is you basically make a new row for the rule. You make the new row by taking the previous one and replacing all the D's by E arrow F's. And finally, we can say, okay, now we have a function that maps E's to F's applied to an E. The right-hand side must be equal to an F. So now we can construct the entire type for S by looking at here, and we say, okay, S, the first argument is C arrow E arrow F, and the second argument is, so we add an arrow between it, we say the second argument is a C arrow E, and the third argument is a C, and the result is an F. Now, because these polymorphic type variables are kind of like free variables, we can rename them if we do it uniformly everywhere. So what we're going to do is we're going to make this a little bit easier to read by saying, look, we're going to change C is going to get changed to A, and E's are going to be changed to B's, and F's are going to be changed to C's. And so if we do that, we get C becomes an A, E becomes a B, F becomes a C, C becomes an A, E becomes a B, C becomes an A, F becomes a C. And so here's kind of like a simplified type. It's a little easier to read. So that's how we can derive the type. We're kind of passing constraints back and forth between the left and right side of this and calculating what the final type of the right-hand side is by introducing types for the different variables over here and refining those. Okay, so what about Cartesian product type? Well, it's actually pretty simple. And as you'll see, there aren't even really any rules if you just write down, if you just transfer the notation for Cartesian product down through the table, you get what you want. But we can also figure out, what if we wanted to add in some functions that we already know the types of? Suppose that F we know is a function from int to bool, and G is a function from int to int. And we want to define H, and maybe it's a little hard to read with it so spread out over there, so I'm saying H of X, Y is equal to F, the pair F of X, where the first element, the pair where the first element is f of x and the second element is g of y. But we know, so when we build this table, we don't just willy-nilly say, oh, f is an a, b, or c or something. We know that f is actually a function from int to bool. So under f, we label it int to bool. Now we still don't know what x and y are, so we label them a and b, so x becomes an a. And we know that g is an int to int, so we can write that type down in here, and b. So now, consider this f applied to x. Since f is a function from int to bool, and we said we assume x is an int, if this expression is going to be well typed, it has to be that x really is an int also. So this is what we're going to call the constrained typing rule, type rule. So if f is a function, and now the thing is that, suppose kind of scoping comes into it right here. Suppose that, I say h of f comma x is equal to f applied to x. Well, then in this case, this f refers to this one. It does not refer to the f which is outside, which we know has type int arrow bool. So it's not the one outside. In this case, since f occurs on the left-hand side of the equal sign, f is a local variable to the function. So we say, if a function, say f, is not the name of any argument on the left side of the table over here, so we're not in this situation. We're in this situation where we're dealing with this h up here. F does not occur on the left, and f has a particular function type, which is applied to a term like x here, labeled by polymorphic type variable, alpha, then generate a new row in the table where every occurrence of alpha is replaced by tau 1. So here, what do? We're basically saying, look, this can't be a, it has to be int, but I have to fix all the a's, so I have to go over here and add int. And so now we could do arrow elimination on f applied to x, or we could apply the constrained type rule again over here because we have a similar situation. And we'll do arrow elimination because it just makes things look a little simpler. And we say, okay, look, in the last row of the table, we have an int arrow bool applied to an int, so that simplifies down to a bool. Everything else stays the same. Now we can apply the constrained type rule to g of y, and we say, okay, look, we know that g is int arrow int, and we know that y is b. Okay, go and fix all the b's and replace them by ints. And finally, we can apply the arrow elimination rule because we have g is a function of type int arrow int. It's applied to an int, so it becomes an int. And now we have, on the right-hand side, a single type expression. A single type expression. We don't have any gaps. And so we know that h is a function from int comma int to, and it returns a bool comma int. So these are the ways, these rules. There's going to be a homework related to this. These rules are the ones that you can use to kind of like in your head scratch out. Or when it gets complicated like S, you might need to take a few like scratch notes, but to keep some notes. And if you practice this, you can figure out the types of essentially any expression that you might run across. Okay, thanks for listening.